And for our final math recap, part 3, we'll talk about Gauss and Stokes theorems. Gauss' theorem relates the divergence of a vector field to the outflux through a surface. So picture some volume element. So we have a surface area A and a volume V, and we can consider a small surface element dA and a small volume element within this volume dV. And for any field Q within this space, we can write Gauss' theorem as the integral of the volume over dq dxi dV is the same as the integral over the surface A q ni dA. And now, so this is the general formulation, and the thing is that Q can be a scalar, a vector, or a tensor. And so in the case where Q is a vector, we can write, if this is the triple integral over the 3 dimensions of the volume, this becomes the divergence of Q over this volume V is the same as the integral of the outflux of Q through the surface that bounds this volume. So the outflux is given by Q dot N dA, where N dA is the normal vector associated with the small element dA. And so this version of Gauss' theorem is known as the divergence theorem. And in words it can be expressed as follows. And so this only works for fully closed surfaces, whereas for surfaces with boundaries, we need Stokes' theorem, which we'll do in a minute. But before I do that, let me just, for completeness, write the divergence theorem in index notation. And there we have dqi dxi dV is qi ni dA. And this will come in handy at several points throughout this course. Finally, we have Stokes' theorem. And Stokes' theorem relates the flux through an open surface to the line integral around the boundary of that surface. So imagine you have some surface that is open, where the boundary C is defined with a direction. Again, we write the area A and consider a surface element with normal vector n dA. And you can imagine this surface might sit in a flow field, U for example, could be the flow. And then the boundary is defined by the tangent, the normal, and a third vector P. And so these three form an orthonormal basis where T cross N is P. And there's a bit of an arbitrariness to Stokes' theorem because you have to pick the direction of what's outside and inside of your surface, i.e. the direction of your normal n. So in this case, Stokes' theorem is written as the integral over the boundary A, over the surface A, of the curl of U is equal to the circulation of U along the boundary C. So the right-hand side here is the circulation of U about C, and this is the curl of U perpendicular to the surface A. So in words, the integral of curl of U perpendicular to A is equal to the component of U that is along the boundary of this same surface A, and that boundary we call C here. And this is actually a way that you define what the curl is. You define the curl of U as the limit of the circulation around an infinitesimal small boundary. So we would write the limit as A goes to 0 of the integral where dA is the same as n dA. So the assumption is that in the limit of a very small surface A, the curl doesn't vary very much, and so you're left with just a constant here. You don't have to evaluate the integral itself, so you have n dot curl of U times A, and then that has to be equal to the right-hand side of Stokes' theorem, which is in the limit of A goes to 0, the line integral of U dot T ds. And so if you divide both sides by A, then you're left with this, which is the definition of the curl of U, where you'd say n dot curl of U is the limit as a area goes to 0, 1 over A times this line integral of the flow around the boundary. And this concludes our math recap.